Hello everyone, and welcome to my channel. This channel is for educational purposes, and we look at theories of everything and their ramifications and how you can use them, especially with your paradigm shifting and your shift to 5D consciousness, formation of your holistic worldview. And today is our 468th day episode that we've covered the reciprocal system of theory from Dewey B. Larson. And Mr. Larson, in 1959, proposed his two fundamental postulates, just two sentences about how he believed the universe operated. Took those two sentences and elaborated them through a process of deduction into a theoretical universe, what his universe would look like if his postulates were correct. And you can find that process of deduction if you go back in the archives about a year and a month ago or so, maybe a little bit more, to about 15 videos that I did called The Outline of the Deductive Development of the Reciprocal System. And then so he took his theoretical universe and he compared his theoretical universe with the empirical measured universe of the legacy scientists, and to see whether his universe matched up with what was so-called really there. And we're looking at the results of one of those studies today called Basic Properties of Matter. This is one of his books on chemistry. And we're about to start chapter 8 today, called Thermal Expansion. He looks at many of the basic properties of matter, such as thermal expansion, specific heat, interatomic distance, compressibility, and many others. And then he arrives at equations for these basic properties, and then plugs in the elements and the compounds into his equations and see what he gets. Now, Larson's two postulates, of them, the first is by far more important. The second is really just what he uses to derive his theoretical universe once he has that first postulate. So the first postulate is the kind of mover and shaper. The reciprocal system is also called the universe of motion, because Larson was one of the few people that attempted to construct his universe upon motion, not matter or not energy, but motion. And so the first postulate reads that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so that is the first postulate. And the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So he uses the principles of mathematics, geometry, and logic in order to derive his theoretical universe from that first postulate about how the universe is made out of motion, and motion is the relationship between space and time, and space, time, and motion have 3 dimensions, and they come only in discrete units. Now, when Larson is referring to motion, he's really referring to what he calls a scalar motion, which which is really a more generalized kind of motion than we normally conceive of. A scalar motion is a motion that has a magnitude, but it has no specific direction. Take a balloon and put dots on it with a magic marker. You blow up the balloon, all the dots are moving away from one another. They are moving in all directions. Every dot is moving away from every other dot. And really every dot is moving away from every location on the surface of that balloon. Every dot is moving in every direction. So it doesn't have a specific direction. Really, the only specific direction you can give it is outward. The balloon is blowing up. It's expanding. If you contract the balloon, then you would say that that would be an inward scalar motion. So scalar motion is either inward or outward. The outward motion he refers to as the progression, and the inward motion would be analogous to gravitation. Now keep in mind that space, time, and motion have 3 dimensions. So when you conceive of this balloon moving outward, it's not a full analogy. You got 3 dimensions of that really going on. And this outward motion, this progression, is omnipresent and eternal, and it occurs at all times in all places, and it occurs in all directions, or outward in all directions. This is what you would call the empty universe. In a universe of motion, you must be able to conceive of motion without anything moving. The motion itself exists before anything that would be moving. So you have to be basically, concede that in order to even get into this world of the universe of motion. Another concept that is a sticking point is the container viewpoint. For thousands of years, we've thought of the universe as space and time as the background or the container of our universe. We go through our drama in the universe on the stage of space and time. Space is this 3-dimensional thing that has a stationary background, and the events unfold through time. And in Larson's universe, space and time are not the contents of the universe. They're not the container of the universe, they are the contents of the universe. Everything is made out of space and time. Space and time do not exist in and of themselves. They only exist together in motion, and motion is what creates everything. So this outward motion of the progression is really the source of everything, and that source is harnessed by reversing the progression. So you take that source, the progression, and first it has to be vibrated backwards, and then it has to be rotated backwards in really 3 dimensions for it to become gravitating. So you're basically, the process of manifestation is basically turning that outward motion of the progression into an inward motion of gravitation. And so that's how you get atoms. And in Larson's system, atoms have 3 numbers. 2 two-dimensional rotations and 1 optional 1-dimensional rotation in the opposite direction. Those 3 numbers, each kind of atom has a unique 3-number signature in Larson's periodic table, and Larson uses those numbers in order to determine his basic properties of matter that he plugs into the equations here in this book. Now also, in all motions are basically fractions, with space or time as the numerator and time or space as the denominator. This is a reciprocal relationship between space and time. You know, the most basic relationship, basic motion that we know of is speed. The bicycle is moving 10 miles per hour. 10 miles of space in 1 hour of time. Space over time equals motion. But all of our other scientific phenomena are also forms of motion, such as matter and energy and force and acceleration and power and pressure and surface tension and permeability and permittivity and electric charge. These are all resistance. These are all relationships between space and time. Fractions with space or time as the numerator and time or space as the denominator. Remembering that space and time both come in 3 dimensions. And, you know, that 3 dimensions of the container viewpoint, 3 dimensions of space, and we're unfolding through time. So space is still, space is still, Larson calls that coordinate space, XYZ coordinates in a still frame, and then time is still progressing in a scalar manner, like on the surface of an expanding balloon. Time is always getting later and later and later, but in no specific direction. So he calls that the spatial reference system. And this is what he also calls coordinate space and clock time. And then by the reciprocal postulate, you know, when you have a reciprocal, all reciprocals have the same qualities, but they are basically just inverted. So there is another place in the universe where there are 3 dimensions of time in a still frame, what Larson calls coordinate time, and there is clock space. Space is the element that is progressing. Space is getting later and later and later, but in the case of space, it's that space is getting farther and farther and farther apart. That's coordinate time and clock space. That is what he calls the temporal reference system, and it's another stationary reference system. But then, but if you have 3 dimensions of space in the spatial reference system and 3 dimensions of time in the temporal reference system, it only requires 1 dimension of motion to describe those. But we have 3 dimensions of motion. And so those reference systems are not sufficient to describe the universe. They, even though they're more convenient to use and that we're accustomed to being in this spatial reference system, it is not sufficient to describe 3 dimensions of motion. Larson has what he calls the natural reference system. And this is a moving reference system. It follows the rate of the progression. And the progression by the discrete unit postulate, where everything comes in discrete units only. The progression is 1 unit of space per 1 unit of time. The progression is always moving outward from every location at all times at the rate of 1 unit of space per 1 unit of time. And Larson determines that speed to be the speed of light. So the speed of light is 1 unit of space in 1 unit of time. The unit of space is approximately 2 millionths of an inch, and the unit of time is approximately 1.52 times 10 to the minus 16 seconds. And that progression of the natural reference system is basically the midpoint of the universe. Half the universe is moving faster than the speed of light, and this is the half that's blasphemous to science. They don't know anything about this. And then half the universe is moving slower than the speed of light. Larson refers to these as the cosmic sector and the material sector, respectively. We really only, reside and know about the material sector, the slower than the speed of light sector, and that is the sector that has your stationary reference system, your coordinate space and your clock time. But the clock time and coordinate space, the clock space and coordinate time is in the cosmic sector. That is the temporal reference system. And when you cross that speed of light boundary, the rules invert and the roles of space and time are interchanged. And now within each one of those sectors, the material and cosmic sectors, there is a subregion, an inside region that also has to do with the discrete unit postulate. Space and time come in units. And so if you have atoms or molecules and they approach each other, they only can get to 1 unit apart of space, or in the cosmic sector in time. And once they reach 1 unit apart, they can't approach each other any closer than that. And so what they do instead is they move further away in time, because time is the reciprocal of space. It appears as if they're moving closer together in space because of the reciprocal postulate. And it appears to us that they're still moving in space because we only see space because we are anchored to the spatial reference system as being, aggregates of matter. And so we see it as they're still moving closer together in space, but they actually are moving in time. Larson refers to this as the time region. And our ability, so within 1 unit of space, there is no space because you have to have a full unit. So you have only time, and that Larson calls that the time region. And that is the realm of atomic and molecular interactions. And there are various impediments that we have to being able to witness that. Not only can we not see time, but what we see, Larson calls it equivalent space. We see the equivalent of what's going on in time in equivalent space. But when we see things in equivalent space, we see only a second power region, and we also see it across that boundary, and there's a lot that's lost in the translation when we look inside that boundary. Also, when we look inside that boundary, the rules again reverse, and now the progression is moving inward in equivalent space, and gravitation is moving outward in equivalent space. And the same thing could be said of the cosmic sector, except with space and time interchanged. 2 cosmic atoms can approach each other to 1 unit of time, but they can't get any closer than that, so they move outward in space. And that is the equivalent of moving outward in time. And so that's how it goes over there. Basically, these are the raw material that Larson uses to, attack these different basic properties of matter. So we're going to start with thermal expansion, see what happens. The basic idea, though, that you want to keep in mind is not that you're going to be able to get at all the details here. There's a lot of details that are too advanced, for a beginner to understand, or even somebody like me who's been studying it a long time to understand. I'm not a chemist, but you're trying to just get the basic principles, pick up some breadcrumbs, because you're dealing with a theory of everything. You're dealing with a generalized theory, and so what the kind of thinking that Larson uses here, he's also going to be using in other fields, and you can use them in other fields. So it's not like you're studying something in a vacuum or in a pigeonhole. You're studying stuff with general application. So, don't spend so much time on whether you understand all the details. Try to get the general picture. Okay, thermal expansion, chapter 8. As indicated earlier, addition of thermal motion displaces the interatomic equilibrium in the outward direction. A direct effect of the motion is thus an expansion of the solid structure. This direct and positive result is particularly interesting in view of the fact that previous theories have always been rather vague as to why such an expansion occurs. These theories visualize the thermal motion of a solid as an oscillation around an equilibrium position, but they failed to shed much light on the question as to why that equilibrium position should be displaced as the temperature rises. A typical explanation, so-called, taken from a physics text says, quote, since the average amplitude of vibration of the molecules increases with temperature, it seems reasonable that the average distance between the atoms should increase with temperature, end quote. But it is not at all obvious why this should be so-called reasonable. As a general proposition, an increase in the amplitude of a vibration does not, in itself, change the position of equilibrium. And I love the way that Larson kind of disarms these sleight of hand tricks that the physicists and chemists use here in this case, where they just say it seems reasonable, but there is nothing reasonable about if something is vibrating around an equilibrium position, then why would it expand? It's going back and forth over an equilibrium position. But the physics, the chemistry, it says a physics text. It seems reasonable that the average distance between the atoms should increase with temperature. Why? It doesn't. So Larson calls them out on that kind of stuff, where normally if you're reading that right from a physics text, you're like, oh, okay, yeah, well, I don't quite get that, but yeah. But no. And so Larson nips that in the bud. And let's continue. Many discussions of the subject purport to supply an explanation by stating that the thermal motion is an anharmonic vibration. But this is not an explanation. It is merely a restatement of the problem. What is needed is a reason why the addition of thermal energy produces such an unusual result. This is what the reciprocal system of theory supplies. According to this theory, the thermal motion is not an oscillation around a fixed average position. It is a simple harmonic motion in which the inward component is coincident with the progression of the natural reference system and therefore has no physical effect. Because the progression is constant, and the progression is always 1 unit of space per 1 unit of time in all locations at all times, and it's a discrete unit, and so it can't be increased or decreased, and so you can't increase the Now, when in the time region, which is what we're talking about here, the time region is really the location of the solid state of matter. And in the time region, you have a simple harmonic motion, and the inward component, because the progression is inward in equivalent space, whereas gravitation is outward in equivalent space. And so it goes back and forth, inward, outward, inward, outward. But the inward half of that is not effective because the progression is already maxed out. The progression already is moving as fast as it possibly can in the inward direction. And so like he says, the inward component is coincident with the progression of the natural reference system and therefore has no physical effect. So the inward motion is canceled out and we only see the outward motion. So I wish Larson would take some more time to explain these things, because he just kind of throws it in one sentence there at the end of a paragraph or middle of the paragraph and kind of leaves you to try to figure it out for yourself, which probably took me 10 readings to figure it out or whatever. So even if that is correct, which I think it is correct, but there could be a different interpretation that I'm not thinking of. But that is my explanation for why this progression is not effective, or why this the inward portion of the simple harmonic motion is not effective. The outward component is physically effective and displaces the atomic equilibrium in the outward direction. From the theoretical standpoint, thermal expansion is a relatively unexplored area of physical science. Measurement of the expansion of different substances, it sounds like he just kind of skipped over, at least I know that he covers this later, but what I would like to say here is the component is physically effective and displaces the atomic equilibrium in the outward direction. So what we basically have is and he says this later, but I'm going to say it now, is that we have an intermittent outward motion. So it goes outward, but then when it goes inward, it's ineffective. And then so it goes outward, and then it's ineffective. So it's basically like it goes out, and then it's ineffective. Then it goes out, and it's ineffective. Then it goes out. So it's an intermittent outward direction. Like every unit of time, it goes out. But then every other unit of time, it doesn't go anywhere because it goes in, but we don't see it as going in because it's ineffective. So we see an intermittent motion that is continually going outward. And he doesn't explain that right there, which I think he would have benefited from. So I know he covers that later, but from the theoretical standpoint, thermal expansion is a relatively unexplored area of physical science. Measurement of the expansion of different substances at various temperatures is being pursued vigorously, and the volume of empirical data in this field is increasing quite rapidly. However, the practical effect of the change in the coefficient of expansion due to temperature variation is of little consequence, and for most purposes it can be disregarded. Most substances expand very, very slowly from temperature. As stated in the physics text from which the explanation of the expansion was taken, quote, accurate measurements do show a slight variation of the coefficient of expansion with the temperature. We shall ignore such variations, end quote. This lack of significant practical application has limited the amount of theoretical attention that the subject has therefore heretofore received. But one of the principal objectives of this present work is to demonstrate that the reciprocal system is a general physical theory. However limited the practical use of the thermal expansion information will be, or may be, we will want to show that this expansion can be explained on the same basis as the other properties of matter, using the same principles and relations that are applied to those other properties, with only such modifications as are required by considerations peculiar to the expansion. In general, the volumetric behavior of a solid in response to the application of heat is analogous to that of a confined gas, the differences being limited to those items which depend on whether the point of equilibrium between any two of the constituent atoms is inside or outside unit distance. At constant pressure, the general gas equation, PV equals RT, pressure times volume equals a constant times the temperature, which describes the relation between the principal properties of the ideal gas, reduces to V equals KT. Volume equals a constant times the temperature at constant pressure. So just equate pressure to 1, and then that's what you're left with. This is Charles's law. It tells us that at constant pressure, the volume of an ideal gas, or one that is entirely free of the time region forces. A solid is in the time region in 3 dimensions. A liquid is in the time has escaped from the time region in 1 dimension, and a gas has escaped from the time region in all 3 dimensions. And theoretically, I think the vapor is what has escaped from the time region in 2 dimensions. Larson agrees with that, but did not ever prove it in his lifetime. And by the way, Larson died in 1990. This book here is from 1987. So, when he's talking about the state of the scientific knowledge or whatever, perhaps it's advanced a little bit since 1987. Perhaps not. Okay, one more paragraph here. The relation E equals PV, energy equals pressure times volume, is merely a restatement of the definition of pressure in a different form, and is therefore valid in the time region inside unit distance. Okay, so I think I missed that end of this last paragraph. The volume of an ideal gas, one that is entirely free of time region forces, is directly proportional to the absolute temperature, the temperature in Kelvin. Okay, we're going to stop there and take over tomorrow at this location. Thanks for tuning in today. And